Oh, good afternoon. I'd like to welcome you here to this event. I think you're in for a very good afternoon. Our speaker today is Donald Pettit, and Don is a native of Oregon State up in the Pacific Northwest and graduated from Oregon State University and received his Bachelor's of Science in Chemical Engineering. And then he decided to go south and got his PhD at the University of Arizona. And after that went to work at Los Alamos National Laboratories as a staff scientist. It was my good fortune to be able to meet Don when he was at Los Alamos, and I've had a good opportunity really to have worked with him for a number of years, even before he became an astronaut. And he was, I think, an outstanding scientist for Los Alamos. But more than that, I think Don is probably one of the most innovative engineers that I've ever had the opportunity to work with. There's one other that probably would exceed Don, and that's Max Vijay, who designed the Mercury and the Gemini and the Apollo spacecraft and then designed the space shuttle. But both Max and Don share a lot of similar characteristics. But Don is more than just a scientist and a great scientist and an innovative engineer. He's an individual that can make things, and he also can take things apart. But usually when he rebuilds them, they work better than they did the first time. And these are great skills, I think, for someone to have coming into the astronaut program. And Don was selected as an astronaut in 1996 and has flown once on the International Space Station on Expedition 6, which flew back in November of 2002. And then he came back to Earth in May of 2003. He went up on the Space Shuttle Endeavour, and then because of the tragic accident with Columbia, came down to Earth on the Soyuz. So he had an opportunity to fly an American spacecraft and a Russian spacecraft. And he might tell you a little bit about the landing that was made in the Soyuz. But Don did some great science on board the space station. And as I say, the skills that he has really made a difference on the space station, because those are the kind of skills that you need certainly when you fly in space, and also as we look at going back to the moon and Mars, they're the kind of skills that you'd like to have there. So hopefully Don will get an opportunity to do that as well. But on the space station, Don introduced a new program. Not only did he do the science that had been planned on the mission, but he introduced a program called Saturday Morning Science. And these were experiments of his own design that he did for fun. And that got to be a great hit here on Earth, because it became very popular with young people all over the country, really all over the world. And so I think we're going to hear something about that this afternoon, and certainly something about flying on space station. So please join me in welcoming Don Pettit.
It's certainly a pleasure to be here at the Baker Institute at Rice University. Being at Johnson Space Center, we're practically neighbors. And I'm going to tell you some stories. I'm going to tell you some stories about doing science. But first I want to start off with my home, which you see up here. It's the International Space Station. I feel very fortunate to be able to call this my home. The International Space Station means something different to almost everybody, and what it is and what we should do with it, there's almost as many opinions as there are people. And I will leave that for a separate discussion. They can be very delightful and exciting. What I'm going to be talking about is how we use space station to do science when I was on board, which was Expedition 6. So it was what we made a space station during that moment of time. The science comes in two different flavors. We have the programmatic science, which is well-planned and well-thought-out science. It goes through peer reviews. It's orchestrated by the ground with principal investigators. And we as astronauts are more like glorified graduate students, and we do the science at the beckoning of the principal investigators. And that's the programmatic science. I'm not going to talk anything about that because I'll let the individual PIs discuss that when they write their papers and give their presentations. What I'm going to talk about is science of opportunity. This is science that we did on space station because we were there and we could. And it was science that tickled our imagination. We saw something that caught our eye, and then we made a little scientific investigation on that particular subject. And that's what I'll show you. And I've got a combination of video, which has mostly fluid mechanic experiments and some mechanical experiments. And then I've got digital still images taken in the vicinity of Earth with scientific things that you can see when you look out the window of space station. And the video, let's see if I show all the video, that goes for 2 hours. And then the slides, I gave a talk at the Houston Astronomical Society, an amateur astronomy group, and showing them all those slides took 2.5 hours. I'm going to talk for a little less than an hour, and then I'll open the floor up for questions. And at the hour point, that's a good point for people to escape if you want to. If you want to hang around for questions, that's fine. A lot of what I have on the video and the slides, I'm going to have to skip through. So if you see something that looks really neat, maybe we'll go over it later. Otherwise, I'm going to skip through the subject so I can keep things within the time period that we have. So with that, let me skip to the video. And I'll start off here. This is the menu that the folks at NASA put together for me. So I have all these different subjects. I can just click on one and we can see it. And we'll start off with making thin water films. Okay, now what we have here is the zero gravity equivalent of a beaker right here. And it's a two-dimensional beaker. Because if you had a normal beaker, if you had a normal beaker, it would slosh out with the open surface area. But if you have a beaker that's really 2 dimensions and the opening is a slit, then you could use surface tension force to keep the water contained. And you can see there, you could just squeeze the bag, open it up, and you could suck in that little errant drop of water. And there you are. Surface tension is your friend here. It can control things. So now what we're doing, this is a 50 millimeter diameter loop of wire, and this water is basically deionized water, so it's the pure water as we have on station. No soap or added surfactant. We pulled that out, and look, there's a film of water. So it's not a soap film, it's a film of pure water. You can't make these down here. And these things are stable. You pull it out here, here's a side view, and this one, you can puff a little more water on it. It's maybe 2 or 3 millimeters thick. But you can use surface tension here at the edge to draw off and drain this film, and you're left with a film that we measured to be about 200 microns thick. And these things are amazing films. They're actually sheets of water. We've had them last for over a month. And look at the reflected light view. No interference colors. Interesting phenomenon going on there that will not allow interference to happen. Here you can get the film oscillating. Look at that. You get these really neat oscillations going in this film. It has a fairly heavy weight per unit area, which you can drive these oscillations. And if you drive it with great enough oscillations, you'll actually spald off some water. So here's droplets in the process caught with a digital still camera of these droplets leaving the surface of the film. And they're different character than looking at splashes of water drops on a hard surface in gravity. Now, once we figured out that we could make these sheets of water, what could you do with them in terms of using them for other science experiments? Well, the first thing that came to mind is to look at diffusion, where you're limited to movement within the plane of the water, and flow perpendicular is basically restricted because it's thin. So what we did here was we put food coloring on this drop of water. The food coloring was to be used to color the frosting for a Christmas cake, which looked a lot like a Twinkie. And so we were using that to look at diffusion. Here's a little cutaway showing what our wet chemistry lab looked like in the FGB module. And it also looks a lot like our shower area on Space Station. And for video backdrops, we either use one of our cleanest dirty towels or one of our cleanest dirty shirts. And here's, again, this sheet of water with this food coloring sitting on it. It's about 200 microns thick. And it just sits there for hours and hours and hours. And you can see the effect of diffusion right on the edge. Watch coming up here. The next scene will be about an hour later. Look at the edges here. See how fuzzy they are. That's the effect of diffusion. But when you puff on it, look at that. You puff on it, you incite some convection within the plane of the sheet, and you sharpen up the edge. You sharpen up the edge of the film. So this could be a good venue to look at two-dimensional diffusion, where flow perpendicular to the sheet is restricted because of its thinness, and you can just sit there with a sheet of water and let it sit there for hours and hours and look at the role of diffusion. Now here we are looking at tracer particles. These are 5-micron diameter mica flakes, and they make an excellent tracer particle to look at streak lines in convective fluid motion. And here we're intentionally inciting a rotational flow within the plane of this thin sheet of water. And you get this flow started like that, and it'll continue for 45 minutes, maybe an hour. It'll just sit there and rotate and rotate and rotate and rotate. Viscous dampening will slowly stop it. And this video will cut into some time-lapse sequences where after the apparent motion has stopped, there's still motion going on in this pattern that you can see if you time-lapse the video. And here's a time-lapse showing where 10 seconds of video time is equal to about one orbital period of 90 minutes. And what happens, this is basically stationary, the structure, but it's rotating a little bit counterclockwise, and then it'll stop, and it'll start to rotate clockwise again. And this is due to the residual accelerations on Space Station. Really neat stuff shows up in this if you look at this as a function of time. And what you learn is you can make a series of these streak lines, and now you can use this as a two-dimensional sheet to study other fluid dynamic phenomenon. And here's what we're doing. We've got a stationary set of streak lines. Here's our soldering iron. And look what's happening. That's called Marangoni convection. And it's driven by surface tension gradients. And what the soldering iron is doing is putting a temperature gradient along this edge, which makes a surface tension gradient. And you have areas of low surface tension and areas of high surface tension, and the fluid starts a tug-of-war with each other, and it incites convection. And what we found was just the heat from our flashlight shining on this would be sufficient to drive convection. So imagine now you want to do a diffusion experiment on Space Station, and you're going to turn on the video lights. What might happen to your diffusion experiment? So even if you're not interested in Marangoni convection, it's something you need to understand, because you could just turn on your video lights and destroy your experiment with artifact. Oh, here is one of these thin films drawn out, made with sodium chloride solution. This is taken from our galley because the salt shaker doesn't work very well in a weightless environment. So the salt is dissolved in water. You squeeze it out on your food. And so I made these thin sheets of sodium chloride solution, and then the evaporation will slowly grow the sodium chloride crystals. And these are time-lapsed over a period of about a day, showing the growth, the nucleation. Here's a little hot spot there where you nucleate seeds, and it spits one off, and then it nucleates another seed and spits them off. And this is a two-dimensional crystallizer because the fluid mechanics is restricted to the plane of the sheet. And so all the fluid mechanics, which is important in laying down the atoms to the edge of the crystal, are governed in this two-dimensional regime. And these crystals turn out to be about 100 microns thick. Every once in a while you get one around 200 microns thick. And you can grow them upwards of 15 millimeters on an edge. You could get cross sections of squares. Some of them are hexagonal, all consistent with a cubic crystal system. Here's the crystal mass after all the sodium chloride has evaporated. And you can reach in there and harvest your crystals. I brought a whole bunch of these home. Now I'm going to have to skip forward. Oh, this is thin film boiling with the soldering iron. I'm going to have to skip that. We'll get into this later. Now, we're switching geometry from thin sheet geometry to spherical geometry. And when you look at these, they'll look like a thin sheet, but really it's a sphere because you're looking at it. And what we're doing here is showing how you make a sphere attached to a wire loop. And what we did was start off with one of these sheets, and then you just keep adding more and more water to it. This is a straw from one of our drink bags, and you squeeze the drink bag, you put water out there, and you can puff up a film into the form of a sphere, and then you could use the sphere for experiments. So that was one way. Here's another way to make a sphere, and you want these things attached to a wire frame so that you can keep them stationary in front of a backdrop and your video camera. Otherwise, they just float all around and they'll stick to the wall. But this turned out to be a rather difficult way to make your sphere because before the surface tension force locks in around the diameter hoop, it's real easy to knock it out of the hoop and it'll drift over and stick on the wall. But look, right here, when it locks in, now that sphere isn't going any place. Surface tension, your friend in a weightless environment, will keep that sphere on the wire loop and you can move it all around. You can use it as a magnifier. And then here's a third way to make a sphere. You just lasso it with you make a free sphere and then you just lasso it with your wire loop. Now look at this. Look what happens when you draw a little water off with your towel. And that's real time. That's not slow motion. You see things that you never see down here as subjects of gravity. Now here's what I call a meniscus lens. Okay, so here is a little bit of an experiment. I want to stop the video so I could talk about it a bit. We have one of those 50 millimeter diameter spheres of water. So it's not a sheet, it's a sphere. Here's some of that tracer particle solution with the mica flakes in it. And we squeezed a little blob of it. It looks bigger than it really is because you got the magnifier, the sphere. That's about a 6 millimeter diameter blob. And the experiment is, let's touch that to the back of the sphere and look at the mixing pattern. We're curious, how are these two things going to mix in a weightless environment? And I want you all to think about how you think they're going to mix. Because what happened, we had these ideas before we did the experiment, and then we did the experiment, and what happened was completely different. We were not able to predict what the mixing pattern was going to be. So with that, let me roll the video. Look at that, a vortex ring. Did anybody think it'd make a vortex ring? When we saw this, our jaws just dropped. It's like, wow, look at that. But then we started to think about it a little bit, applying some of the surface chemistry that we learned in school, and pretty soon we could figure out an explanation for why it makes a vortex ring. But we had insufficient imagination before we did the experiment to realize that that was going to happen. And I think this is a good example of why we like to do experiments in the first place, because a lot of times you don't know what the answer is going to be. It's not in the back of the book, and you do experiments just so you can make some primary observations. Here is the needle injecting tracer particles through the interface, and once through the interface it just looks like a smokestack sort of thing. So it shows that there's something magic that happens when you go across the interface. Now, this experiment is called our big sphere. And we're going to make a free sphere of water that's the size of my head. Okay, and this is in the process of making it, so let's watch this. See, there it is. It's about half the size of my head there. It makes a good magnifier. Okay, there it is. It's about the size of my head. I was trying to get my face behind there, but there wasn't enough room between the sphere and the cleanest dirty shirt there for a backdrop. And it's probably a good thing, because you can imagine if I would have got behind that sphere with the magnification effect on my nose, it would have been pretty scary. But what can you do with a big sphere like this? The thought pattern of why do you want to make a big sphere? If you look at the ratio of surface tension force to inertial force or body force, that's going to decrease the larger the sphere becomes. So that's just a fancy way of saying the role of surface tension force compared to all the other things that can make a sphere oscillate and wiggle around will become smaller the larger your sphere becomes. And you look at spheres that are maybe the size of an egg or a golf ball, and there's been many experiments and examples of these on past flights. But to make a free sphere the size of your head, I'm unaware of folks making something like this. And another little story behind us. This occurred after Columbia, and we were in a water shortage, or I should say a water conservation mode. And to use this much water just for a silly little science experiment, we weren't sure we wanted to use that much water, so we were really careful not to lose this water. And then when we were done with the experiment, we sucked the water all up, put it back in drink bags, and we made tea out of it, so we were able to drink our experiment after we were done. But the idea now is what's going to happen here when we put a delta function pulse on the side of this sphere and drive it to oscillation. Now, so what we have here, here's this sphere. We've let it sit for a long enough period of time to get in a quiescent state. Here's a syringe. And this is a special syringe. It's an irrigation syringe. So instead of having a little fixture to put a needle, it's got a big orifice on it right there. That's 6 millimeters in diameter. And I timed it with a stopwatch. I could put a 10 cc puff of air out in 100 milliseconds. And so what we're going to do is give a 10 cc puff of air on this sphere, radially directed from about 2 centimeters. And let's look what happens. And we'll see this a couple times. I mean, again, when we saw this, our jaws just dropped, which is kind of an oxymoron, because in a weightless environment, your jaw can't drop, right? I mean, it's just amazing what's going on here. And that was real time. And we're going to see it again 2 more times in slow motion. And I'll try to describe what I can see in it, but I hope that folks here can maybe see things. So look at that. Puff forms a crater, ejects a drop. Surface waves go around. It's like throwing a rock in a pond, but it's a spherical pond, and the boundary condition forces the waves to stay on the outside of the sphere. They come together at the antipoid. A big spurt comes out. Surface tension makes it collapse, sends surface waves back over again. So you get this delightful combination of surface waves, meanwhile, body waves or inertial waves that make up a classic spherical oscillator are superimposed on all of this. The surface waves dampen out, and you're left with the body waves. Now, when I first saw this, oh, there we go. We stopped it right there. When I first saw this, I couldn't help but think about computer models I'd seen when some hapless planet gets whacked by an asteroid. And so look at this. There's a big impact crater, right? And there goes the moon. It just formed the moon. It just spalled off a drop, and then comes back, and it makes a big bruise on these impact basins in our solar system. You'll find a bruise 180 degrees on the opposite side from a planetary body that has a big impact basin on it. So there you go, planetary impacts just from a big drop of water. Oh, this is the inverse system now. We have a sphere, a big sphere, this is about 3 inches in diameter, with a big bubble inside. And we're driving a spherical oscillator now, but the boundary conditions are just inverted from what we saw. Instead of a drop of water surrounded by air, we have a drop of air surrounded by water. Different boundary conditions, different behavior. And of course, we were so fascinated by this, we filmed this many, many times. This is in slow motion. Here we go again. You could drive these delightful oscillations in the air bubble. Again, a different version of a spherical oscillator. And trying to make a big free air bubble like that in a weightless environment is easy, but when you have gravity around, it's really difficult to make something like that. Now look at this. Here we're doing our bubble oscillation experiment, but look what we found inside of the bubble. What is that? We found we could generate droplets inside of the bubble, inside of the sphere. And so we decided, let's investigate the droplets. So here we are, just directly injecting droplets inside of the bubble, inside of the sphere. And this became our Symphony of Spheres experiment. And again, it just makes your jaw drop. At least it made our jaws drop to look at the dynamics going on there. Look at that. You see droplets ricocheting all around. There's a three-body collision right there. It's like a three-dimensional game of billiards. But wait, there's more. You'll see droplets accelerating. You'll see droplets absorbing each other. You'll see droplets getting momentum. Like, what happened there? I mean, how did it get momentum? So this was something that became a study in its own. And I filmed hours and hours of video of this stuff happening. Now, watch this droplet. It can bounce with the wall maybe 4, 5, 6, 7, 8 times, and then there will be a mass transfer. Boom, like that. And when there's a mass transfer, it imparts momentum into the droplet and it jets it off the wall, and it'll bounce around again 4, 5, 6, 7, 8 times, and then there'll be another mass transfer event. So what's happening here? What kind of dynamics is causing this to occur? Could you write a proposal? Before you saw this, would you be able to write a proposal and get NASA money to study this? It's something that you almost have to just be there and do and look at the dynamics. Now watch this. This droplet, it's going to have a mass transfer right there, and we're going to see a slow motion version of that. If you look carefully, you'll see that there forms a little neck, a little connection, and water is pushed from the droplet through the interface into the surrounding. And the process of doing that, it acts like a little jet engine or a little rocket engine. It pushes the droplet off of the surface, and it gives it momentum, and away it goes. Now here's another one. You could get these droplets to roll around on the inside of the bubble in circular motion. And circular motion creates creates a radial acceleration, or you could consider artificial gravity. So the next thing to try to think about is, can we intentionally roll these droplets around? And then let's look at the behavior. And here's an example of that, where a droplet like this will rotate around for 45, maybe 50 seconds before it gets absorbed. And what's determining when you get this absorption event? Why does it go for 45, 50 seconds? Why doesn't it just get absorbed after 15 or 20 seconds? Why does a drop have to collide 4, 5, 6, 7, 8 times before it gets a mass transfer event? These are all questions which I'm still scratching my head on. I don't really have a good explanation for this. But look at that. You see, it had a mass transfer there. And then the resultant drop bounces around. Here's one going in and out of the plane of the video. And these things will just roll and roll and roll, which brings up an interesting question. Are they rolling like a ball over carpet? Or are they sliding like a hockey puck? And if they roll, that connotes some form of friction, because something can't roll unless there's friction. But we have a fluid-fluid interface. And there's this engineering constraint called the no-slip boundary condition, which basically says you got frictionless flow at an interface. So how could these things roll? So they must be sliding like a hockey puck. At least that's what we initially inferred. Here's some with red food coloring so that you can look at the fate of the drop. Now look at this guy. And you tell me, is he rolling? Well, so how do we explain that? Because it should be a frictionless surface. Whoops, there he goes. Now, I'm going to have to move on here. Here's rotating sphere filled with bubbles. Really neat stuff. Rotating flask with bubbles. One of my favorites. Okay. Okay. This, I have to say, this is an effervescent antacid tablet. But from a science point of view, this is a great example of heterogeneous bubble nucleation, which is a fancy way of saying you're forming bubbles at a solid surface, which is different than homogeneous bubble nucleation, where you have bubbles forming uniformly throughout the volume of a fluid. And to investigate that, a good example would be something like a bottle of champagne. Unfortunately, we didn't have anything like that on station, so we were not able to do the homogeneous bubble nucleation experiment, and we had to settle for the heterogeneous bubble nucleation experiment, which is interesting because when a bubble forms at the surface, it can get momentum from the surface and actually move out with some finite velocity from the surface into the surrounding fluid and create some really neat bubble dynamics. I thought, does anybody have any idea what's going to happen? We came up with two ideas, two models, theoretical models before we did the experiment. One, you have your effervescent acid tablet, bubbles form on the surface, they coalesce and form a gas pocket. And now water can't get to the tablet anymore, quenches the reaction. So we called that the gas film quench model. And then we came up with another idea. What happens if the bubbles form on the surface, they don't coalesce, so water can continue to get to the surface through all the laminae between the bubbles, forms another row of bubbles underneath that one, they get pushed out, and so you just get this expanding bubble foam. And we decided to call that the expanding spit bug nest model. But it turns out not too many people have seen spit bugs. I guess they don't live here in Texas. Where I grew up in Oregon, we had spit bugs all over the place. And I found that people just couldn't identify with spit bugs. So we decided to give it another name. We called it the expanding beerhead model. And I found that most people could identify with that one. So those are the two models we came up with. Then we decided to do the experiment, and we were wrong. Something else happened. So with all of that, have an idea in your mind what you think is going to happen. I'll roll the video. We'll see this twice. A little hiccup on my CD player because it stops if I talk too long. Okay, there we go. Look at that. And I've seen this many, many times. I've got hours of video of different attempts at doing this. What looks like, to me, I like to call it bubble war. And what's happening, bubbles form and they eat other bubbles. And in sort of a cruel act of nature, big bubbles eat other bubbles at a faster rate than little bubbles can eat other bubbles. So the big bubbles get big and the little bubbles get eaten. And you end up with this bipolar world here where you have two super bubbles. And all the little bubbles are pushed in between, kind of like the whale hurting the krill in a big thing, and then they just take turns and they eat them up. But if the bubble's too small, they don't eat them. They have to wait till the bubbles grow a certain size before they'll get eaten. Here we'll see it again. And watch what happens. Bubbles form at the surface. They get expelled off because it's a heterogeneous system, right? You get momentum. They move out into the volume. They rapidly coalesce. The big bubbles grow bigger. They eat other bubbles. And you get into this situation where you only have a few big bubbles eating all the other bubbles. And you see these little tiny bubbles can just swim around. Nobody's going to eat a little one. But they get to a certain size, and then they get gobbled up. So here we have a world now with maybe 3 or 4 big bubbles. There's a big bubble. It'll get eaten. Okay, there's another big bubble there. It gets eaten. Okay, now we're down to 2 super bubbles. Look at that. You can see between them. Pretty soon we're going to be down to 1. There we go. And you have this cloud of little bubbles. Almost looks like a little world on itself. Now, being an engineer type, you want to ask yourself, how can we remove all these bubbles in a weightless environment and get back to the original sphere? So we put that syringe in and sucked out that center gas pocket. And now we use radial acceleration as our friend. And we stir the bubble up. And we're going to send all those bubbles to the center. And it makes a little tornado bubble core. And then you can stick your syringe in there, and you can suck those bubbles out. And if you work at this long and hard enough, being good engineering types, you can get back to something close to what you had when you started the experiment. See, look at that. You get all that little bubble core, you just go in there and you vacuum it out. And now you're back to close to what you originally had. And then here we're going to have a towel suck all that off. Look at that. Capillary action, again, is an amazing thing in a weightless environment. Okay, oh, viscoelastic fluid, really neat stuff. Sorry, we won't have time. Here's a little setup that shows how you make one of these films, and you have a little table, a camera cantilevered off, and there's your cleanest dirty shirt for a backdrop, and we're looking at bolts. I was fascinated by bolts, and this is kind of a uber geek sort of thing, but look at this. We're looking at the exchange between rotational momentum and linear momentum. This bolt, look at it. It's rotating fast, but it's translating slow. Suffers an elastic collision. Look what happens. Boom. Translates fast, rotates slow. Classic textbook example without gravitational artifact for momentum exchange through an elastic collision. And I did dozens and dozens of these things, and they're really interesting, but I think we'll move on to another subject. Oh, here. We couldn't help but notice that our compact disc player made a fairly decent gyroscopic platform. And that's just from the rotating disc inside. And being sort of engineer types, we wanted to figure out what we could do with these. And here's one that's turned off, and it just freely tumbles about its center of gravity. And there's one turned on. And again, being engineering types and having a couple of these, we decided to make a 2-axis stabilized gyroscopic platform. So that's turned off, and now look, here it's turned on. Look at that. 2-axis stability. Now remember, we had 3 crew and 3 CD players, so what do you think the next experiment might be? There we go. So 3-axis gyroscopically stabilized platform. It's turned off. Give it a little push. Freely spins about its center of mass. Now it's turned on. Look at that stability. Now, I've showed this to one group of students, and someone asked me if we had heavy metal discs, whether that would give more stability, and I don't quite think so. I think that was country western. Now, what can you do with this? Being engineer types, you tape your flashlight to this platform, and now you're going to work behind some dark panel on space station with your drill, and you're going to need 2 hands. So what you do is you use your gyroscope to hold the flashlight. You can listen to music, and then you can get to work. Okay, now, I'll just show a short little bit of video here, and this is kind of a setup to show how we do it. Here's one of these little photography arms. Here's a little flask. This is a 250 milliliter flask filled with bubbles and water. And we can orient it different orientations with respect to the geometry on space station. And then you can do time-lapse video at the microgravity level and look at how the bubbles move around. And we're going to see just a little bit of this. And it varies with, see, all the motion you see here is due to the residual acceleration at the microgravity level on space station, where 10 seconds of playtime is equal to 1 orbital period of 90 minutes. Look at that. And it's amazing, even at the microgravity level, over time, small objects will move considerable distances. And this goes into a little more detail than what I'll go into here, but it depends on the orientation and attitude of space station. With your experiment, you get different behavior in the bubbles. Some bubbles will go around. Sometimes the bubbles will go around in circles. Sometimes they move in straight lines. It depends on the magnitude and direction of the residual acceleration. Okay, oh, this is sodium chloride crystals in a big Ziploc baggie, and you shake it up, and look how static electric forces bring them together into floccules about the size of your fist in tens of seconds. And this actually has relevance to planetary formation, and we were featured in a National Geographic special on planetary formation on how you get dust grains to form fist-sized objects so that self-gravitation can make them into planets. Oh, rotating moments of inertia. Oh, great stuff. We're going to have to skip that. Oh, let me show a few minutes of this. My watch broke on orbit. The crown came off, and then one of the buttons fell off. And eventually I found the button on a vent filter after about 3 weeks. So we decided, let's go ahead and take the watch apart and fix it. And I've done a little bit of watch repair as a kid. And I figured, let's just show folks that we're not bulls in a china closet when we're on space station working in a weightless environment, and we could do the epitome of fine watch repair on orbit. And so I filmed this video showing all the stages of taking this watch apart, and then we actually were able to get it fixed and running again and put back together. In some respects, working with all these little tiny parts is easier in a weightless environment than on Earth. Whoops, sometimes you lose your battery. Let me go here. Okay, this is snack time. On station, you take a break every once in a while, and in Russian tradition, you have a snack with honey and black bread and tea. And so this is just an example of how you go about having a snack. And here's our galley table. And there's the little black breads. They're bite-sized loaves of bread, so you don't need to worry about cutting a loaf of bread and making crumbs. And then this is a can of miot, which is Russian for honey. And we're opening up that can. And the Russian food, they don't put Velcro dots on the Russian food. So you have to figure out how to hold it on the table. And we're going to use surface tension, which is our friend here. And we put a little drop of water right on the bottom of the can. And then you can just stick it to the table. Voila. So you don't even need to have Velcro. And so there's my chopsticks. I eat many of my meals with chopsticks. And there are those little loaves of bread. They're perfectly scaled down loaf of bread to the size of a Barbie doll. And so we referred to those as our Barbie bread. And they're really tasty when you dip them in that Russian honey. Look at that, a tractor beam of honey pulls the loaf back in. And then this is a real treat. And now what we're going to do, we're going to drink some tea. And this is a tea, that's a straw from the tea bag, and I'm squirting some tea out. And you can eat your tea with chopsticks. So look at that. You just squirt the tea out. And then you can grab it with your chopsticks and you can eat it. And it's really quite an elegant way of eating your tea. Here you have a nice spherical blob of tea, and there's your chopsticks. And look, surface tension is your friend. And you can just sit there, you can pluck these little spheres of tea off your straw, and you can just eat them. Oh, and notice, hemispherical profile right there in this free can of honey. Neat stuff. And again, this might be one of the better uses of all this surface chemistry I learned in college. And you can eat your tea with chopsticks. Now, I had one student, when I challenged them to try to do this here on Earth, they said, well, you just drill a hole down the center of one of your chopsticks, and then you can use it like a straw. Oh, peanut butter. We could do this. Peanut butter and honey is really tasty stuff. Oh, look, they're losing a cracker right there. We'll find it against a filter sometime later. And so now you mix the peanut butter with the honey. And this is really, really tasty stuff. And you only maybe get to do this treat once a month when you're on station. So it's really important to be able to have your honey mixed in with peanut butter. So you ever have something like that staring up out of your peanut butter and honey here? Yeah, I like to say that in space, you can play with your food and you can call it science. But don't tell my kids that. And then you just dip your cracker in there and, oh, it's really yummy stuff. Well, let me shrink this back down and go on to some digital still slides here. Okay, we've already seen that one, picture of my home. This is an example of what a full pass through Earth's atmosphere can do to an object when it gets close to the horizon. This is a mosaic of the moon when it sets. And you think about when we see an object like the moon set, we're only looking at a half a pass through the atmosphere. But from orbit, you look at a full tangent line going through Earth's atmosphere. So the distortion you see is qualitatively different than what you would see if you're standing looking at it with just your eyeballs on the surface of Earth. this is a total solar eclipse. We were fortunate enough to see one of these guys, and you can see the umbra and the penumbra right there. It's just like in the textbooks. It's amazing that people were able to figure all this stuff out. And from our vantage point here, you could see all the classic examples of spherical projection of shadows on another sphere. It's amazing. This is a mosaic, a Starfield mosaic that we took in the southern hemisphere. Here's the Southern Cross right there, and here's the Milky Way, the Coalsack region, Eta Carina. And I like to use this to show that the platform we've made on Space Station, although it wasn't designed to do astronomy, the control moment gyros we have on station do an amazing job of holding station attitude. And you can take pictures like these, of the Starfield pictures where the stars are nice little pinpoints. You could do this on this orbiting platform where the control moment gyros are holding station attitude. And so this is not something that we intentionally thought about doing on station, but it's something that that you can if you want to use station this way. Here's a different kind of amateur astronomy picture. This is taken 90 degrees to your direction of motion, with Earth being right here in the limb. And this picture shows atmospheric air glow. The atmosphere glows kind of a greenish yellow color. And for lack of a better term, people decided to call it air glow. And you can see it with your eyes when you're on orbit on the dark side of a pass. You can measure it with scientific instruments on the Earth, but you can't really see it. So people have known that there have been Airglow, that the Airglow has been there since the 1920s. But to actually see it is just an amazing thing that you can do as a human being. And you can take pictures of it, and you can actually see different layers in the atmospheric Airglow. And I've got dozens of pictures of Airglow, and I won't go through them right now, because you got to be kind of an Airglow geek in order to really enjoy these pictures. But there's a lot of neat structure you can see in the Airglow, which shows up from these kinds of orbital perspectives. Oh, one thing to look here, Earth is scooting by here pretty fast, and look at these flashes. That's one thunderstorm as a function of time. So it's like a flashbulb going off in a room, and then it waits a while, and then another flashbulb going off. And you can see that there's structure from flash to flash, and it moves around a little bit. There's a lot of really neat physics in this one picture. I can talk about it for about a half hour alone. Really neat stuff you can see if you just look out obliquely at Earth and the atmosphere. Now, cities at night. Cities from orbit at nighttime are amazingly beautiful. I think they may be one of the most beautiful unintentional consequences of human activity on the planet. Amazing. And everybody that goes into space tries to capture them on film. And you get pictures like this. That's Long Island right there. This is Montreal. And these pictures are a little bit soft in focus. They're 1, maybe 2-second exposures. And the way you do this is you have to have the camera, you're floating over the window, and you get the camera moving so it cancels out orbital motion, and then you click the shutter and you hold it open for 1 to 2 seconds, and then and that's how you get these pictures. And so the focus has always been a little bit soft. And that's the best that we were able to do. And we were kind of disappointed in that. So we decided maybe we could make a machine to help us out. And what we found out was in one of the closets was the mount for the IMAX movie camera. And how many folks here have seen the IMAX movie Space Station? A number of folks. Well, many of those scenes were filmed with this mount, but we didn't have an IMAX camera on station, and we figured they won't mind if we use it a little bit. And so we took it out of the closet, and we put a couple cameras on it, and then here's a long threaded bolt that we borrowed from the Progress vehicle. It's an unmanned Russian spacecraft that comes up and docks, and it brings supplies. Then we fill it full of garbage, and we undock, and then it burns up in the atmosphere. And we figured, since this vehicle burns up in the atmosphere, it's not going to miss one little bolt. And so that's the bolt for progress. Here we have our little drill driver, and we could vary the speed on the drill driver, turn the bolt at a different rate. It pushes against the platform, so we have one direction of gimbal that is very precisely controlled. And you line that up to the velocity of motion on station, and then you look through this camera. This is a Hasselblad camera with a long lens on it, a telephoto lens, and that's just a fancy telescope with a nice big friendly eyepiece and a big reticle. And you squeeze the trigger on the drill until the cities are stationary, and then you take a picture with this Kodak Nikon camera here, our digital still camera that we use on station. And so with this little piece of equipment, let's see if the video, yeah, this video shows it in operation. So there's the drill, it's turning, taking pictures with a cable release on the digital still camera while looking through the Hasselblad. And you can only move it so far, then you got to stop, back up, point it in another city, and then you can keep doing that. And if you're an amateur astronomer, you'll recognize that this isn't anything more than a glorified barn door tracker, which amateur astronomers use on Earth to take pictures of space. And I found it interesting that we were in space using a barn door tracker to counteract orbital motion to take pictures of Earth. So anyway, here's the picture of Montreal. We've seen that. The best we were able to do with a handheld camera. The next picture will be the same field of view of Montreal with this barn door tracker. And so and once we got this technology in place, we took about 2,000 images systematically all over Earth. And of these cities at night. Some of them are beautiful, big urban areas, but we took a lot of images out in the middle of Congo and Amazon and places like that where you'd only see a few little pinpoints of light, and it makes an interesting database worldwide of where human beings sprinkle their lights circa 2003, and how they distribute their lights, and how these patterns of light are imprinted by your social culture. So let's go through and look at a number of these. And let's see, how are we doing at time? Oh, we've got about another 10 minutes, and then we'll be at the hour point, and then we can take a break. People can escape, and we can open the floor up for questions. Here's the St. Lawrence River, Montreal. Here's all these neat bridges going through. We go to Montreal a lot for training, Canadian Space Agency, training to learn how to fly the arm. This is the downtown region of Montreal, and the Canadian Space Agency is down here. In this region, there's a real nice hotel. It's called the Elizabethan. We've never stayed there. Near this interchange is a hotel, a Motel 6. And recognize this place? That's Chicago. And I'm just going to go on a sort of a whirlwind tour around the world right now. This is New York, Long Island. Look at that. You can see Central Park. It's dark. There's Times Square. It's lit really bright. They're still figuring out the receipts from the day's exchange. This little spot right there is where the World Trade Center used to be. They were still in the process of either reconstruction or deconstruction. That was going on during our flight. If you blow this up, you can see the Statue of Liberty, or at least the little pip that makes it. You can see Ellis Island. And there's a bridge down there someplace that I guess is for sale. This is Tokyo. Now, notice it's a different color. There are color differences in cities as you go around the world, partly due to the ratio of parks to gray cement, but partly due to the choice of street lighting. And so this looks sort of like mercury vapor, where other places that were orangey are probably sodium lights. This is Sao Paulo in Brazil, big industrial area. Here's the coast. But look, here's the old part of town, and it's kind of blue-green. And then here are the newer boroughs being developed, and they're sodium vapor. Lots of neat cultural patterns start to come out when you look at how human beings sprinkle their light bulbs at nighttime. This is Milan in Italy. And this is neat because Europe looks different than, say, North America, than America when their cities at night. North American cities, you see a north-south, east-west grid, and here you get in the countryside in Europe, and you almost get this Mandelbrot fractal space in terms of how the cities how the lights are scattered out at nighttime. This is in Iran, central Iran. Not a whole lot of lights, but some very bright lights. These are probably flares from gas fields. Here's a little village. This is Abu Dhabi in the United Arab Emirates. The cities in the Middle East are just amazingly beautiful. Lots of kilowatts of lighting on the streets there. Multicolors, very high contrast because you don't see a lot of clouds and fog and things like that. Very beautiful cities from orbit. This is Riyadh, capital of Saudi Arabia. Again, beautiful cities from orbit. This is El Paso. And this typifies the difference between U.S. cities and Latin American cities. And you could look out the window and say, Latin American city. You can just tell by the way the lights are. You look out, U.S. city. You look out, that's Europe. Asia has a particular character all its own. But here's the Rio Grande going right through here. So this is all El Paso, and this is Juarez. And notice the whole urban area of Juarez is lit up. And that's typical of Latin American cities. Don't know why, but the whole urban area is lit up like that. This is typical of American western cities, where you see the major streets and freeways, but it's basically dark in between. This is New Orleans. And Lake Pontchartrain is along here. And here is the Mississippi coming down through here. There's the French Quarter. Looks like there's a lot of activity there, even though it's the middle of the night. And then it comes on out here. Recognize this place. This is Houston. And it's oriented so north should be close to being up. Here's Galveston down here. Look at that. Here's I-45 going up. And there's a little skip of fog. When I first saw this, I thought, I didn't have the camera focused right because it's kind of soft. But I looked at it, and the focus is actually good. It's just, it was one of these nice foggy nights here in the middle of winter in Houston. Here's the 610 loop, right? And that's probably, what, 288? And I guess we're probably all around here. Down here's Clear Lake, and there's NASA Road 1. And notice the Space Center, it's pretty dark. And then you go up here, there's Space Center Boulevard and Bay Area, and there's El Dorado, and my house is right there. Now, anybody figure out where this is? This is Washington, D.C. And I found this amazing. Look at this. You can see the outline of the District of Columbia in light. I mean, what's going on there? Is this guy here in D.C., he's got 27 lights on, and this guy in Maryland, he's got a Coleman lantern or something? You know, what's going on here? If you're driving on the ground, you can't see any difference. It doesn't all of a sudden get dark as soon as you go into Maryland. But from space, you can see this. And I like to use this as an example that from space, you can see political boundaries. But look at this. Here is the Congressional Mall. And they were doing work on the Washington Monument right there, so it was lit up. Here's Congress. If you blow this up enough, there's the Lincoln Memorial, and here's the Jefferson Memorial. Here's the Memorial Bridge. This dark area, that's Arlington Cemetery. See this dark area here? That's the Pentagon. They're trying to be covert by turning all the lights out. It's amazing the kinds of structure that you could see. Going up the eastern seaboard, here's Washington, D.C. again. Look, there's Baltimore. And you can see the outline. And I pasted in the city boundaries from an atlas. Look at that. The city lights match what you see for the outline of the city limits. Amazing little fades show up. Don't know why, but you can see these fades from space. And not all cities you can see this kind of a border on. Only some cities you can see strong delineation when you come to the edge of town. I was talking to some folks back in Washington, and they noticed that the images of Washington, D.C., they're pretty bright. And Washington, D.C. is a very well-lit city. And they were thinking that it's got to be the brightest spot in the world. And I had to correct them. I said, Washington, D.C. is not the brightest spot in the world. This place is. This is Las Vegas. And look, and this is, again, typical of a U.S. western city, north, south, east, west grid. You get to the edge of town, and it's just dark. And in between the major streets, it's actually quite dark. Even though you might not realize it, being here in Houston, when you look up at the night sky, it's actually quite dark in between the major city streets. And then look at this. Here's McCarran Field. You can see the airports. They start to show up as these big, dark fades. And then here's the strip going on there. So, gosh, I've been talking too long here. We need to open the floor up for questions. But in summary, I've had a wonderful experience to be able to call Space Station my home. We can do a number of different, the space station has a number of different purposes depending on who you happen to be talking to. Everybody seems to have an opinion for what we should be doing with Space Station, and it makes lively discussion. During our mission, we had a fairly well-defined purpose for what we were going to be doing or what we did, and a good portion of our time was spent doing science. We spent some time doing construction. We spent a lot of time doing maintenance. And of the science, we had some moments that we could do scientific investigations on our own. And we called this Science of Opportunity, or our own form, Saturday morning science, so people wouldn't confuse the science we did with the programmatic science. And I've showed you a little bit about fluid mechanics, had some mechanical experiments, had some digital still images on what you can see when you look out the window. And that wraps up what I have to say about Saturday morning science. And this is a good time for people to escape if they need to. If you want to hang around for questions, I'd be happy to entertain questions on Saturday morning science or any other aspect of living and working on Space Station. So, any questions? Yes, right here in the front.
Okay, you have the crew exploration vehicle very slowly getting put together. I'm concerned the shuttle is now scheduled for July, August, a launch attempt, and I don't know if it's still going to be satisfied with the tile problem. Is there any possible mixture of external launch vehicles that can take the rest of the station components up and then just construct them, using Soyuz personnel transfer vehicles? I'm thinking, what happens if the shuttle just can never pass safety requirements?
That's an interesting question. The question basically is, if we can't get the shuttles flying, can we get the rest of the parts of the space station back up? And the short answer to that question is I don't really know. It's something worth thinking about, and I have heard that there are folks that are thinking about it, but I don't know what their conclusions are yet. But it's a question that's worth asking.
Another question: the crew exploration vehicle. I guess there's some merger talk between Boeing and Lockheed Martin, and they still have two designs and two manufacturers. Do you know how that's playing out? Are they just going to go to one, or are they still going to insist on two?
Oh, wow. I'm just a simple astronaut type that flies in space, and you're asking me manager questions. I have no idea really on the contracts for getting the crew exploration vehicle done, but good questions. I'm just the wrong guy to answer those. Yes, back here.
How long were you up, and then kind of what was your recuperation process when you came back?
How long was I up, and what's the recuperation process? We were up for 161 days, so 5.5 months. It was going to be one of the shorter missions on the books, and then Columbia happened while we were up there, so we expanded to one of the longer missions. So that's sort of the mission in a nutshell. We have a whole set of folks working on countermeasures to try to preserve the integrity of your body from the effects of long-duration space flight. And we haven't answered all the questions, but we've done a lot to advance our understanding in this area, particularly through doing hardcore physical exercise. We spend 2 to 2.5 hours every day working out through a combination of cardiovascular and weightlifting exercises, which is kind of an oxymoron or a misnomer. When you're in a weightless environment, you do weightlifting, but NASA engineers are smart. They figured out a way to do weightlifting when you're weightless. And the combination of doing these things, crews are coming back from a mission on space station in better shape than they've been coming back before. So we're making progress. We're not completely there yet. There's more work that needs to be done, but we're making good progress in that area. Yes?
Are those pictures that you have, is it possible to access them from the internet somehow? To look at?
Yes. All the pictures and video I showed are part of the space program, and as part of NASA, they're all available to the public. So that's the good news. The bad news is you got to know how to find them. And have you seen, like, the end of the movie in Raiders of the Lost Ark, where they're putting that Ark back in that big government warehouse? That's kind of like archiving things at NASA, and you could find them if you know how. And they're all available, and yes, you could do them over the internet, but be prepared to take half an afternoon to figure out how the system works. And there are tutorials that will tell you, and it could be a little bit frustrating, but persevere. You'll be rewarded by getting some amazing images that you can use for either just hanging up on the wall or for scientific study. It's worth investing the time to learn how to do it. Yes?
It will also be archived at the BakerInstitute.org, so you can see them the whole presentation.
Yeah. The video that I showed was video that some folks at Johnson Space Center helped put together for me. Actually, they put it together, and I was helping them. And it doesn't have an audio track. And we're in the process of laying an audio track so that if you see this green stuff getting squirted all over, you kind of have an idea what it is if I'm not there to tell you. And so when we're almost done laying the audio track, and when that's done, we're going to gin out a bunch of copies. And I'll make sure that the folks here at the Baker Institute get a copy of that DVD with the soundtrack on it.
What's it sound like? What's it sound like to be on the space station?
Oh, the space station, it's noisy. There's lots of fans and things. It's kind of like living in an engine room on a ship. Maybe not quite that loud, but there's always a background drone. All these fans and things. It's almost like you're living inside of an organism. And it becomes kind of comforting after a while because there's all this noise and you're used to it. It's just part of your environment. And then when the character of the noise changes, that's when your ears pick up. Like the pitch that a fan makes, when it changes, it's like, whoa, what's going on there? And then you find out there's a big dust bunny stuck in the turbine or something like that. And so it's changes in this ambient noise that you really key into as a crew member. Way in the back.
How do you determine when to sleep, when to wake up?
Oh, well, you get tired, you have 16 orbital periods a day, and so it's always getting dark, it's always getting light, it's always getting dark. But the station is run on a Greenwich Mean Time schedule, and you get up in the morning, you have a meeting about 7 o'clock in the morning, we have a powwow with the ground, and you figure out what you're going to do for that day, and then you go about doing it, and they will schedule you for about 12 hours worth of stuff a day, and you never can get it all done in 12 hours. You're probably working more like 14 hours a day, and then any other moments, that's your spare time for doing whatever you want to. And so you're on this schedule, and by the end of the day, you are beat. You're tired. You float into your sleep station, and within 5 minutes, I'm sawing logs. You sleep really well on station. Yes?
The introduction mentions your return to Earth on the Russian. What was that like?
That was an interesting experience. We spend a lot of time in Russia training to fly their spacecraft. So, because used during our day. It was supposed to be a lifeboat in case you had to come home. And so you have to know how to row your lifeboat. So we spent a lot of time in Russia learning how to fly the Soyuz spacecraft for the descent phase of flight. And so we were well versed on how you use the spacecraft. We didn't know at the beginning of the mission we were going to be using it, but that's just the way it unfolded. And so flying home in the Soyuz was not that big of a deal because we were well trained for doing it, and we just jumped in, and it was like one big simulation, and the next thing you know, you're on the ground. We did have a little malfunction coming in where we were actually flying serial number 001 for a new upgraded cockpit, where many of the modifications were enhancements to the descent phase of flight. And we had a little trouble coming in, and we downmoded to what is called a ballistic entry. Normally you have a piloted entry where you can actually fly your spacecraft in. You can choose which direction it's going to go, and you can choose your deacceleration profile and land where you want to land. And when you switch to ballistic entry, you're basically coming in like a personified meteor, and you have no choice on where you're going to land, and you have no choice on the deacceleration profile that you're going to have. And we trained for this in Star City a lot. So the fact that we did a ballistic entry wasn't that big of a deal from our training. We did land off course, and they lost us for a while. We knew where we were, but they didn't know where we were. And we were someplace in Kazakhstan was where we knew we were, which is a pretty big area. It makes Texas look like Delaware. So it took them a few hours to find us. And while we were on the ground, we crawled out of spacecraft and deployed our survival gear and set up some radio beacons and got our food and water out and did a few things that showed that we weren't just quivering blobs of jello. We could actually do some very basic tasks immediately at landing.
I'm curious, did anybody talk about carrying one of those iridium phones for such things?
After our mission, they carried an iridium phone. But we were so far away from any place that even the radio we had a VHF radio, which has a line of sight, maybe 150-mile range, and there wasn't anything around that we could even talk to. So an iridium phone, now the crew's coming down having an iridium phone. Yes, way in the back.
Was your health routinely monitored during the 161 days?
Oh, yes. The flight docs and the BMEs, they are your friend, and and part of the experiment on space station is the knowledge they can sort of pry from your own soul, and you have to be able to take that with a sense of humor. But there's all kinds of experiments and or tortures that folks do to you, and they're good. They're really well-planned experiments that are worth doing, and we're slowly learning a little bit about how human beings function in a weightless environment, and that in itself has two implications. One, if you know how to function in a weightless environment, it can help you do long-duration space missions, so it's kind of self-serving from that point of view. But it gives you a good venue to look at human beings in a non-typical environment to see how your physiology responds. And you can learn interesting things. That's how we do experiments. We put something in a different setting and see how it behaves. And there are things that you can learn by doing that. And that's another one of the long-range aspects of doing life sciences research is the long-range knowledge that you can gain from human physiology, which ultimately could be used to help folks live better lives on Earth that never leave the planet. And one example I like to use on that is scurvy and the discovery around 1750 that if you sucked on citrus, you could alleviate the symptoms, or you could alleviate scurvy. And so at that point we had an operational cure for scurvy. Suck on citrus, you won't get scurvy. Wow. End of story. You could go off sail around the world, no problem. It was about another 150 years before folks discovered about vitamins and diet and the real fundamental nature of scurvy. And so there's two levels of discovery there. One is you got to learn how to operate your saline ships and keep your crew healthy. But there's the other implication of learning the physiology of these vitamin deficiencies. And when you learn about them, now you can keep people that live on continental Europe at that time, you could keep them healthy from these discoveries you make. So it's important to continue fundamental research into these aids. At the same time, you end up with an operational, empirical-based cure that allows you to go out and do the explorations. Yes?
How exactly does the process of becoming an astronaut candidate work?
I get asked that question a lot, and the short answer is you put in an application. And because nobody's going to pull in front of your house in a limousine and men in black come out and invite you into the program. The only way you'll get into the program is to put in an application. By the way, the application you fill out for astronaut, it's the same general application for a civil servant. So if you want to be a postman or a firefighter or anything like that, it's the same application. And then NASA has a few extra sheets that they have you fill out. But the basic application package is the same thing that you do if you want to work at the post office. And you fill out the application. You keep your application current because they only go through selections maybe once every 2, 3, 4 years. And they'll accumulate all these applications. They may have 6,000, 7,000 of them on file. They'll close, look at everyone they have, go through a selection process, choose 12 people, and then they'll start it over again. And so you need to keep your application current and keep it in and don't take no for an answer. It took me 13 years of keeping an application in before I finally got selected. So just put an application in, don't take no for an answer. Yes?
Your recycling modes, do you know how much there's any thought to try to make the station a closed loop system, with agricultural type CO2 and oxygen generation?
The question has to deal with how closed do you make your life support system. And station has a number of life support systems that close some of the loops. The gas loops, from a technical point of view, are the easiest ones to close. And those are ones that you typically close first. And you can't ever 100% close one of these things. There's always a little bit of purge, a little bit of loss in any of these separation processes. But you could do a pretty decent job of closing the gas loop. We generate our own oxygen through electrolysis. We scrub CO2. We filter micro contaminants out in charcoal beds. So we have all these little chemical plants in there that purify the air. We strip out the humidity. We call it condensate. And then we recover that and we make it into dinner the next day. So I like to tell folks that yesterday's sweat and breath is today's dinner. So we do a fair amount of recycle right now. When you get into recycling body waste, that's a whole different category of chemical processing required. And people have been working on this, but it's not quite at a flyable stage yet. We're gonna be close, and I think in a few years we're going to be trying it on space station. And I've suggested to the engineers that have designed this equipment that will recycle our urine that they need to put one of these pieces of equipment in their building, and all the coffee that they make, that they drink at work, needs to come from that machine, and they need to do that before they put it on station. But anyway, that's the people just grin at me when I suggest that. And then closing the food part is probably the hardest, and it takes a lot of square feet to generate your own food, and food can be made and squished down pretty compact when you compress it and freeze dry it and shrink wrap it and put it in little pouches. So closing the actual food part of the loop is probably not going to be done for a while.
Can you recycle your CO2 scrubbers? Can you heat them up, release CO2 and use them again?
Yes, they are recycled beds. The Russian process has 3 beds with a zeolite, and 1 to 2 of the beds are being in use, while the other bed has a vacuum purge, and then they just alternate them back and forth. And then the U.S. process is similar, a zeolite. We heat our beds and have longer cycles because it takes a while to heat the zeolite up and then cool it back down again. But you can expel more of the CO2 that's absorbed if you go through a heating process. So different optimizations, different cycle times, but basically the same process. Let's do another question. Yes?
Two things. The first, regardless of what space station is or is supposed to be, I just want to say thank you for what you made it when you were there, because I think this is very inspiring work. So I want to say thank you. And then two, based on the crew size now, obviously 2 people don't have a lot of extra time, but are there any plans based on the success of your Saturday morning program to continue that on into the future?
There are plans. The crews that have followed me have done Saturday morning science in the time periods that they have had to devote to this. So it's still continuing on. There is still some science that can be done at the discretion of the crew members, and I hope to see this done again, because you can use laboratories in a way that's commensurate with how we use laboratories on the ground. Because you look at a laboratory, whether it's at a university or at a industry or a government research laboratory, you've got some programmatic work which pays your salary and all the equipment and everything. You're in that lab doing the programmatic work, but because you're there and you can, and you dream up these little ideas, you can run off and do discovery science on your own. And this happens all the time in laboratories here on Earth. And I think we can get a greater return on what we can do with space station if we have that same model where you have very necessary programmatic work that goes on, well planned, well thought out, but at the same time you let the folks that are up there chase some of their own technological rainbows. Just because they are there and you've got some spare time and you can do that. Yeah, one more right here.
Okay. Did you bring up a Saturday morning science kit with you, or did you just kind of make it up as you went?
Yes, yes and yes. I brought up a kit of stuff with me, and as crew members, we're allowed to bring up a small bag about like so of personal effects. And many people bring up banners from their university. There's probably been a rice banner on station. They bring up things like that. They bring books up, pictures of family, whatever. I brought a chemistry set up, or things that you could use for experiments. I didn't really know how I was going to use them at the time, but I figured you needed a good collection of syringes so you could meter and accurately measure and squirt fluid out. So I brought a bunch of syringes. And I knew that the doctors wouldn't like it if I raided the medical kit. So I brought my own. And then most of the other stuff you just find, Ziploc bags and stainless steel safety wire and soap and things like that. You just make do with what's on station and whatever tickles your imagination. You got the basic tools there and you charge off, and next thing you know, you got a Saturday morning science experiment.
Well, thank you, Donald. I think that was a great talk, and I appreciate it very much.